So next, we'd like to look at the effect of the leaving group on an SN2 reaction. So the leaving group, of course, is the group that leaves after the nucleophile attacks. So overall, we can say a more stable leaving group will give a better SN2 reaction. But how do we gauge what's a better leaving group? Well, in general, we can look at basicity. And as we know, if something is a weaker base, that means it's less reactive. If it's less reactive, it's going to be more stable. And if it's more stable, then in general, that will be a better leaving group. And so we can see an example of that here. If we compare I minus, Cl minus, and F minus, three halogens. First of all, which one is the strongest base? Well, we can determine that based on the pKa of the conjugate acid. So the pKa of HI is approximately -10. For HCl, it's approximately -7. And for HF, it's about 3.2. So what that means is that of these three possible leaving groups, their conjugate acids, HI is the strongest acid. Whereas HF is a weaker acid. What that means as well is that I minus is a weak base, whereas F minus is a stronger base. We wouldn't want to call it a strong base. It's still significantly weaker than something like hydroxide, but we wouldn't want to say that it's a weak base either. If it's a weak base, it's going to be a good leaving group. F minus, which is a much weaker, comes from a weaker acid and is therefore a stronger base, ends up being a very poor leaving group. And one way that we can illustrate that is by looking at the relative reaction rates. So if we define the rate at which F minus is able to function as a leaving group, we define that as 1. We find that if chloride is our leaving group, that's about 200 times faster than fluoride. And for iodide, which is an even better leaving group, it'll react about 30,000 times faster. So in general, what we're looking for are things that are weak bases. The weaker the base, very likely the better the leaving group. So what does that mean for things like hydroxide, OR minus, or anions of amines? Well, hydroxide, we know, comes from water. OR minus would come from an alcohol. Their conjugate acids are around 15 to 20. Whereas NR2, its conjugate acid, depending on what the R groups are, could be in the range of 30 to 35. So both of these are strong bases, the oxygen anions as well as the nitrogen anion. And so in general, these are, both OR minus and NR minus are often poor leaving groups. That's not to say that we'll never see them as a leaving group, because in fact, there are reactions where we will see, especially hydroxide, as a leaving group. But it's not a good leaving group. In addition to that, other than some very unusual circumstances, R minus and H minus are almost never leaving groups. They're too strong of a base, they're too reactive, and therefore we will basically never see those as a leaving group. But the one that really sticks out to us here is hydroxide. And the reason for that is if you start thinking about the number of functional groups we have, how many of those functional groups contain oxygen? Well, the short answer would be a lot of them. There are a ton of functional groups out there that contain oxygen in them. And so we will learn a lot of reactions that go sort of back and forth through different oxygen-containing functional groups, or where we need to be able to add or remove oxygens. And so in order to do that, sometimes we need to get oxygen to function as a leaving group. Now, how do we do that? Well, there's a couple different ways. The first method is to use acidic conditions. And this method has both positives as well as some negatives to it. On the next slide, we'll get into another method. The positive here is it doesn't end up being a separate reaction. It's something that you could add to your reaction conditions. The negatives we'll explain as we get into the reaction. So in this reaction, we take something like an alcohol and we add an acid catalyst to it. Now you'll notice, and this is going to happen more and more, I'm going to start drawing our reaction arrows as equilibrium arrows. And that's because pretty much every reaction is actually in equilibrium. So if we add acid to an alcohol, the lone pair on the alcohol will attack the H+. To give us something that looks like this. Now, just like we said with nucleophiles, that a negative nucleophile is always better than its neutral counterpart, the opposite is true for leaving groups. A neutral leaving group is always better than its negative counterpart. And that's what we've done. We've taken the leaving group, which would have been hydroxide, and now by putting a proton on it, it's positive. But when it leaves, because it takes the electrons with it, it'll become neutral. So what happens now when a nucleophile comes in? So a nucleophile can come in and kick out the leaving group. And we get our SN2 reaction. And we can see what our leaving group was here was water. So by adding that acid, we went from a poor leaving group, hydroxide, to as stable of a leaving group as we could possibly have, something like water. Now, what are the negatives of using this method for making oxygen into a better leaving group? Well, there's two major drawbacks. One is that you have to add a strong acid. And that strong acid may not be tolerated by other functional groups. What do we mean by that? So an alkene, such as this one, in general won't affect an SN2 reaction from taking place. We could have a nucleophile add in here, kick out the bromine, and the alkene doesn't care. But what if we had this alcohol and we added acid here? So will it do what we want? So it very well may protonate this alcohol. But remember, we learned a reaction at the end of organic 1, the hydration reaction. One of the ways to hydrate an alkene is with strong acid. And so that could also happen here. And so you may end up that the alkene reacts instead of the alcohol. Carbon being less electronegative than an oxygen is more likely to be willing to give up its electrons. So one of the things we have to start to concern ourselves with as we learn more and more reactions of different functional groups is what other functional groups are present, and can they be affected by the reaction conditions? So that's one drawback of using strong acid. The second drawback is under acidic conditions, we are limited to neutral nucleophiles. If we add a negative nucleophile, which is a better nucleophile, then that negative nucleophile is likely to just react with the acid and nothing will happen. So this type of thing can be used in some situations. But because of these two issues, you have to be very careful. So we look at a second method. And this is what we use more often with alcohols especially, is to convert them to a better leaving group. And many of the common leaving groups will end up looking like this. So we replace the hydrogen with this sulfonate group. Now, what is R here? Well, it turns out R can be a whole bunch of things. Probably one of the best leaving groups out there would be to make R as CF3. And this is known as a triflate, or abbreviated TF. R could also be an aromatic ring with a methyl group at the other end. This is another very common one known as a tosylate. Why is it that these are better leaving groups? Well, what do we have after these groups leave with the oxygen? We get an anion that looks like that. And that anion, as you hopefully recognize, is a fairly stable anion because the negative charge that's generated by it leaving can be delocalized to the other two oxygens by resonance. And then depending on what you choose for an R group, that can make the leaving group even better. And so we said triflate here is one of the best leaving groups that we have out there. And that's because your negative charge is not only stabilized by resonance of the other two oxygens, but you've also added 3 electron withdrawing fluorine groups. All right, so how do you make one of these sulfonate groups? Two common ways that are actually fairly similar. And we won't get into the mechanisms of these two reactions today. These reactions actually fit very closely into a class of reactions known as nucleophilic acyl substitution. They're not exactly examples of those types of reactions, but they're extremely similar. And so when we get to that topic, that's probably a good 5-6 weeks from now, we'll come back and revisit that mechanism. But we use a reagent in this first case known as triflic anhydride. Very, very reactive reagent. I believe you actually have to store it in a glove box. In other words, you can't expose this compound to air at all. So this is actually a compound that has 2 of these triflate groups with an oxygen in the middle. And then you need a base. And these are usually amine bases that you use in the reaction. Things like triethylamine is a common example. You don't need a very strong base in these reactions. And as a result in this reaction, it will convert your alcohol into a triflate, and that triflate can be substituted very, very easily. For the tosyl example, instead of using an anhydride like that, we use a sulfonyl chloride. And then again, an amine base. And then the group here ends up substituting for the hydrogen, and we get our tosylate. Once you've made these compounds, you can easily use them in an SN2 reaction just by adding a nucleophile to them. And many of these sulfonate leaving groups are actually as good as, say, iodide. And iodide, as we'll learn, is already one of the best leaving groups that we have out there. So we have one more property to look at for SN2 reactions, and that's to look at solvents. But I'm going to stop this video because I normally try to not go too far over 20 minutes on these.